I'll start. I want to speak about a topic having to do with software engineering and particularly uh, ensuring quality within software engineering, which has come up quite a few times, both in discussion with student teams on the incremental deliverables, as well as in class. And I wanted to uh, articulate some general principles and guidelines for use of methods that handling situations where things go bad, um, where there's problems that arise in code. And we've talked in class and to some degree in the team meetings about a number of ways of doing so, of handling these situations where things don't go according to plan. Exceptions has been one technique. Use of return values has been another. We've talked about use of assertions that flag us to problems within the code. But there's been some ongoing puzzlement, I think, on some students' parts, judging by the questions, as to where these techniques are each applied, and indeed where additional techniques, such as the use of monadic values, might play a role. So I wanted to grapple with this issue today, and to do so despite my infirm condition. So I'm going to share my slides here, and are you able to see those slides? Oh, that isn't any good. Are you able to see those slides?
Yes.
Okay, thank you. Okay, so when we build software, much of our mind inevitably lies on the case where things go according to plan. The expected case where our software can deliver value to stakeholders. The case where user entries are within expected range and our software can do its job. Cases where we have enough memory, enough disk space, where network connections don't drop out. In cases where other components of our system work together seamlessly to cooperate in order to allow the software to work properly. Now, while our mind is on this case of delivering value when things work properly, it's incumbent upon us, it's our obligation as software engineers to handle many inconvenient but undeniable problematic cases. And one of the messages that I want you to carry away from today's lecture is that these problematic cases are not just all undifferentiated nuisances, this inchoate group of situations that are inconvenient to handle. They fall into different types and to different categories, different classes. And those different classes often need to be handled in different ways to make our system performant, extensible, modular, but also sometimes just to deliver proper quality for our code. Now, just to list a few types of examples, there's end user errors, Problems where resources that we count on, be it networks, memory, database connection, disks, or indeed good access to CPU resources, don't hold up. They're unavailable. There are failures like network failure or disk failure, disconnection from a database, or they're in contention. There's much other demand for a CPU or for a network or for a disk, and things go much slower than expected. There are times that the files we count on for our software to work properly are subject to corruption, where the format isn't what we expect. It isn't what we wrote out last time. And there's cases of programmer oversights where people from elsewhere in the team, or indeed elsewhere using our components as building blocks for their own projects, may use our code in ways that fall outside of its scope. And finally, and critically, there's cases where end users, interact with our system in unexpected ways that we didn't anticipate, ways that don't allow our system to deliver value, but where we have an onus to handle. We have a responsibility to still be able to respond to that user in a graceful way. And I want to talk today about 4 problem handling approaches that are appropriate under different circumstances when inconvenient, problematic circumstances arise. It's not one size fits all. Some of these techniques are used under very specific conditions, and those conditions differ. The classes or categories of problems for which these are best suited will differ. And the trade-offs differ. Trade-offs in terms of special language support for them. Whether they appear in end user code, for example, will differ. So I'd like to talk about each of these 4 types of issues, not in the exact order here featured, but going through each. I'm going to start with perhaps the one that's likely to strike you as the simplest. It's the one that perhaps students learn about and practice earliest in their careers, and that's the use of return codes. And, within this circumstance, when things happen, and I'll be returning to some of these examples later, if we want to duplicate a string and we run out of memory, we indicate with a special return code that this inconvenient thing has happened, that we've run out of memory. And in the case of pointers in C, or mutatis mutandis in the case of languages offering references, which are allowed to be to indicate no reference with a null value, we return null, for example. Or, an example that I gave you earlier, cases where we're trying to find one string and another. You may recall you working to try to build up a specification with respect to this. We're trying to find one string in another, and we need a way of indicating this possibility that this string being found does not, in fact, exist in this other string. If it does exist, we return the index at which it exists in there, can be found in there. But if it doesn't exist, we need some sort of distinguished way of saying, hey, it's not here. And traditionally, we've done so with these return codes. So here we indicate for this language returning a -1. And this practice goes back decades, and it probably goes back to some of your earliest experiences with programming. We pick out a special value that indicates something has not worked, for example, right? And even in Linux, created, atop of the Unix design, this is standard in return codes for programs that indicate whether they succeeded or failed. 0 being indicated to use failure. And that builds on Unix conventions from the 1970s. This is a venerable technique, and it's very common in the canon of programming practice. So, we have a special value EOF that we return when we reach an end of file. Or if we reach the last item in a linked list, we want to indicate it, that we're at there's no further item. Or we want to indicate a file not found, or item not found in a data structure. These are common occurrences. If you call this function, you expect that sometimes this string will not be found, and that's one. And you need a way of signaling it, and signaling it in a way that's lightweight, that doesn't take much processing power. It doesn't require expensive data structures to be maintained, or to be viewed as an emergency if it's not found. That requires a lot of work. So return codes provide this balance. Excuse me. They're lightweight, they're simple, but there's some issues with them. They serve a kind of simple function within our programming, but one of the issues is the handling is not enforced, right? If we can return null, it's possible that the thing that called us is not going to be expecting that, and it doesn't handle it. Or in the case of common programming on Unix, does 1 mean success, as in like true, it succeeded, or does 1 indicate failure? And something like 0 indicates success, as is the case when you have Unix utility. 0 indicates, okay, it succeeded. So this issue of inconsistent interpretation is an important issue. And sometimes if there's more than one return value, don't just have end of file or you return a character, you have others. You need to be able to interpret the results. And often, there's also a desire to capture some sort of data about what was going on at the time, what happened. That's a little bit more textured. So, to handle some of these concerns, conventions in language support have come up. So in many modern languages, for example, the C family of languages, and this carries over to for example, Scala, and I believe Rust, if I'm not mistaken. We can use enums to clearly delineate different enums to delineate values. Haskell is something similar, that giving sort of a designated set of possibilities that's clearly defined. And these are defined with types. And that can allow us to make sure that we're returning a value that's legitimate given the set of possibilities. You can't just return any old int, for example. And they can also allow us to ensure that we're handling all possible values when that is returned, that we're not overlooking a possible value. And there are ways to do this and to help enforce the proper handling of these return values. In earlier languages, we have practices of doing things like pound defining return codes. We pound define OK or pound define EOF to be a specific constant. And then in our code, we can return EOF. And that's clearer than code that returns, the value 2 or something. It's clear what the intention is behind it. Over the years, programmers also built up conventions. For example, if you have a language where there's an uninitialized value in variables of a certain type, maybe it's a value of 0, you define that as an illegal possibility, so that if you get that, you know that something's broken in your code. You know the programmer didn't return a real value, they returned an uninitialized value. So we sort of delineate sets of possibilities where we have one of them that is explicitly set to be the value of an uninitialized variable. So if it's ever returned, we know, hey, something's wrong. This is not being handled properly. Now, this goes a certain distance, but there's a limit to how much type safety and enforcement we can have for many languages when we handle these values. In some cases, there's not a kind of what I'll term a canonical value, or a really well-defined distinguished value that's the right one to return. It's somewhat up to programmer convention, right? So for that find first function, like I described this using returning -1, but we could have returned min int, which is some minimum possible value that an integer could take on. I say integer because it returns an int. And the fact that I returned -1 is a little bit arbitrary to why I didn't return min int. You might think, well, maybe it should be the least value below the legitimate values, and that's why I chose -1. But there's nothing canonical. There's nothing like totally distinguishing about it. Nothing that makes it obviously the right choice. And that's a bit uncomfortable. Now we're thrusting it into the area of convention. We'd like to have a clear choice that is obvious and that guides our practice. There's a deeper issue with composition and what are termed higher order functions. When you have a function that takes another function as a value or returns a function, it turns out that return codes don't play very nicely in that context. I'll just highlight that we like often to have pipelines of logic within programs. And I won't go into most of these, but sometimes we'd like to be able to find agents within a certain range of a point and then ask for how many of them are infected. Or we have a collection, we want to filter it by some criteria and ask for the mean income over that group. Or maybe we ask for the nearest agent and we send them a message. And if one component of this pipeline fails with a return code, it makes it infeasible typically for the rest to continue in any way. And if this can either return a reference to an agent or some return code like null, we are not going to be able to continue this operation with null, and it will cause an error if that happens. Similarly, if we filter by this and we can't find anyone in that range calling me, and we return something like null, we can't call mean income on it. It will lead the pipeline to fail. So the failure of any one component leads the whole pipeline to fail. And similarly, when we have composition by nested calls, so we call square root and we take the reciprocal of that square root. If square root encounters a problem, maybe we take square root of -1, and then if it were to return some return code, then we can't take the reciprocal of that return code. We're counting on it being a value, a double precision value. So in modern day data science, we can secure great economies, great efficiencies, and great clarity and modularity out of building up pipelines of things strung together. But this use of return values that can return something that's an impossible value flies in the face of it. It breaks those pipelines. And these pipelines are actually critical in many cases for performance, for achieving effective performance. Now, we're going to come back to that. But first, I want to hit on arguably and equally important, certainly one of the most dominant of paradigms within today's programming landscape, which is the use of exception. So I would argue return codes are handled, are commonly used for common events which we need to signal something especially for. They may not be the best way to handle them. We're going to come to monadic ways of handling them, but exceptions are a very popular, language supported, and prevalent type of way of handling inconvenient values. And where these really are best employed and where you see them used is rare events that are unexpected. Not common events like, oh, you've hit the EOF. Not common things like, I couldn't find that string in this other one. But cases where something exceptional has occurred. Maybe it's a network disconnection. Maybe the database connection has been dropped. Something that causes you to have to rethink in a big way what you're going to do, that you have to handle as an exceptional circumstance. And exceptions are supported by languages, many of them today, although some more advanced languages eschew them in favor of more monadic approaches. They recognize their grievous limitations that can sometimes come in. So we're focused here on things that are exceptional. I listed some of them, but a few more here, right? Disk full. There's a corrupt file. Memory is exhausted. We can't simply punt and not handle these things. To be responsible as programmers, we have to handle them. To do otherwise can mean corrupting the data for our users or causing our users to be unable to use the system from now on, or getting the wrong values or what have you. So we have to handle them. We don't have the option of just punting and say, well, someone else's problem. But they're rare enough that efficiency concerns often retreat. And it's important that we handle with it when we're going to use this somewhat blunt instrument of exceptions, this somewhat awkward mechanism of exceptions. We recognize the cost involved, and I'll be coming to that it comes at very high computational cost. It also comes at a high cost to reasoning about our systems, although we won't have time to go into that as much. Oops. Excuse me. So in this case, we are going to be recognizing that during execution of blocks of code, things can go wrong. And we want a way of handling and signaling that stops the processing of code, and it returns to a kind of safe context where we have some sense of how to proceed. And often that's further up in the logical chain. We may be way down there in some logic having to do with database queries and handling of result sets from databases. And suddenly we get an indication in the middle of this logic involving dealing with return values obtained from the database and assembling them into data structures, maybe in an ORM context. Suddenly our database connection is not available. So in this case, we might use exceptions to return to a context where we can deal with more user-facing, like end-user-facing issues, where we have knowledge of how to clean up after this, of how to gracefully signal that we can't continue this querying, and potentially back off some and retry in a little bit, or indicate to the user that this particular time the database is not available, we wish to reconnect. Or maybe it's a matter of waiting, I was saying backing off for a minute or two and trying to reconnect to the database. But we might want to log some things about the circumstance, and we might have some data structures that have to be cleaned up, that we've gotten ready to get this query, and we need to dispose of them in a sensible way. Maybe we need to close some files. Maybe we need to deallocate some larger data structures that we've allocated. So the idea here is that we have a smaller context in which the problem occurs, and we want to bubble up to a context where we have the option of handling it better. And in this context, many languages, Java is one of them, uses exceptions. And the idea is that exceptions are thrown where they occur. Where there's a problem, they can be thrown, and then they're caught in handlers where we wish to handle certain types of exception. And we may have certain handlers for a subset of exceptions that we handle at one point, and then the thing that called that might have handlers for additional types of exceptions. So I think the basic syntax here, right? We have some try block. We have some code within this where we're trying to get some work done. And we have a separation of concerns here. We write this code for the kind of typical case. And if something goes wrong there that throws an exception, maybe we try to open a file on disk that's expected there, and it can't be found, and that triggers an exception. Or maybe we are calling off to a database to submit a query, and we get back an exception for network timeout or connection it's disconnected. Or maybe we're calling off to some smaller function within our code base that throws an exception from it that it doesn't know how to handle. And we can have a catch block here that catches certain exceptions and handles them that we wish to catch. And if we don't have a catch block, so the fact that we've caught it means that we are dealing with it. If we don't have a catch block for a certain exception type, it will bubble up to the thing that called us. And if that doesn't have a catch block, it will bubble up above that, to the thing that called that on the call stack. So if F calls, this is where I'd write on the board if we were in class, F calls G, G calls H, and H has an exception, it goes back to G, it kind of bombs out of H for this unhandled exception, goes back to G. G says, I don't know how to handle this, and it goes back to F, the initial thing that calls G, and maybe F has something to handle that. So exception handlers provide this dynamic way. It's at runtime. We can determine where things are to be handled in this call stack as we call them. And we can bubble up to the point where somebody knows how to handle this disconnection of a network connection, or how to handle this corrupt file, or how to handle this disk full error. It doesn't require that handling at all minor levels of the logic, all detail levels. It can bubble up to the point where it's known. And there's some language innovation that's occurred over the years where, you can have common blocks that handle common logic for the try block and any of these exception handling components. And I should emphasize in these exception handling, sometimes what they do is they handle a given exception that is more detailed, and they bundle up the information into a more general exception and throw that up to be handled by higher levels of the logic. So we have a try block, we have a catch of various sorts, and different exceptions may need to be handled in different ways. So, for example, I'm trying to get this thing out of your way. So we have a try block, and maybe it throws a number format exception. It's trying to here get a next integer from a file that it's reading. And maybe there's a problem with that number format. You're looking for an integer and it found something that has a decimal point in it. Or maybe there's something about an index out of bound that occurs when I try to find out a particular agent that is at one of these numbers, and that will be handled differently. So there's a certain separation of concerns that come here by handling different exceptions in different ways. You can kind of deal with one type of exception at a time, and it can be handled by somewhere else if it's not right to handle it here, if you don't have the requisite knowledge of context to handle it here. So languages for decades now, really since, there were hints of it with set jump and long jump in C in the 1970s and 1980s, starting then. It may have started in a slightly later revision of C. C++ had exceptions as a key mechanism, and since then you've seen them in language after language. They offer some benefits that have been trying to emphasize, allow you to focus on the kind of core code, the typical logic, allow you to handle exceptions of different types in different try blocks or at different levels of the system, recognize that at the most detailed level, you might not know how to handle an exception somewhere else does. But these come with big costs. And the foremost, a key cost, one of the key costs is performance costs. They are not free. They have big costs associated with them. And if you use it for common circumstances, like I can't find this string and that string, which might otherwise seem sensible. Hey, it's an exceptional thing, right? It's not the normal thing we expect. You might be forgiven for thinking, or end of file, or to signal something with being at the last element of a linked list, or what have you. That might seem sensible at some level to someone who's not aware of these costs. But these costs can be massive, and they can have a foremost impact on slowing the performance of a system. People have accidentally stumbled into this thinking, well, this is an unusual condition. I'll handle it with an exception. That's how you do things in this language, and turns out to be problematic. Now, there's other, and why is that? Why are they so expensive? Well, one reason is if you have an exception within, I said, F calls G, G calls H. If you have an exception in H, I mentioned this bubbling up process, and that's an expensive process. It has to kind of blow out of H back to G, and has to somehow blow out of G back to F. And that unraveling of that stack is expensive. So yeah, A calls B, B calls C, and I have to be able to blow back up there. But what's often more expensive, or what also adds expense, is in order to allow for that to happen when it needs to, there's complex data structure set up, an A and B. So when they call C, if C throws an exception, it will have to make use of these data structures. So there's behind the scenes engineering that's going on just in case an exception is called. And that can exert costs as well. You have this lots of extra mechanism and work that goes on. Now, there's some more subtle costs too. One of the most pernicious ones in languages like C++ or C with set jump and long jump is the occurrence of memory leaks. If A calls B and B calls C, let's suppose that B allocates some memory. And gosh, maybe C also allocates some memory. And then C realizes, like, something's gone wrong, something's gone terribly wrong, and it throws an exception. Unless you're really careful and in these exception handlers to free up that memory, it may stay allocated. And suddenly you've lost the pointer to it. You've lost the reference to the memory you allocated, because you've bombed out back to C, and you can't free it up. And so this is a memory leak. It's memory that was allocated, but now you've lost reference to it, and it's just going to sit there occupying space for no good reason. And over time, if this happens too much, you maybe get more and more of your memory chewed up in ways that are now inaccessible. Even worse, B may call off to C without an exception handler, and C bombs out with its exception. It rips through C. C doesn't have an exception handler to it, goes up to A, and the memory allocated by B, without an exception handler to clean it up, as this thing bombs back from C, and goes back to A that called B, because B doesn't have an exception handler, that memory is also, references to that are lost. Similarly, suppose that B opened a file and C throws an exception. It rips through B, goes back to A, B never closes that file or never closes that database connection. Right? If you have resources that you've opened that need to be coordinated, need to be cleaned up, need to be closed, you often lose that chance. Now, there's some additional software engineering concerns. Sometimes you look at this code, it's not clear where it can bomb out with an exception, right? One point I'll tell you is here. Another point is here. Another point is here. But it's not clear. And the kind of code to handle these situations is distributed, right? Like the code to handle the getting a next integer, and if there isn't one available, is distributed between here for sort of the normal case and here for the unusual case. And that makes for some difficulty in reasoning about the code. You're not quite sure, whence, from what place here you've come here. And so it can be hard to recognize these mistakes in code. It can be hard to recognize cases where, resources need to be closed. You've forgotten about them because you didn't realize, it can occur after a point where I open that resource, I open that file, or I open that database connection, or I allocated that memory. It turns out that we'll come to this issue with the Liskov substitution principle to understand that better, but there can be violation of subtyping rules. If A calls B, which doesn't say what exception, that it throws an exception, but B calls C as part of its implementation. A doesn't know that B calls C, but it does, and this one could throw an exception. Really, that should be indicated by B, but in many languages, including Java, these so-called runtime exceptions, A's not going to know about it. And so A could get this exception it doesn't know about. It calls off to B. That should be a contract it has between A and B. And instead, some aspect of B's implementation that it calls C throws a wrench into it. It throws off this exception. Now, over the years, we've had ways of trying to deal with these things. Garbage collection, ownership-based memory allocation models like in Rust, forcing declarations as part of the method, declarations of B, for what exceptions it can throw, and enforcing that. So if it calls off to C and C can throw an exception, if it doesn't, either it needs to handle it or it needs to indicate in its own exception statement, in its own declaration, that it can throw off this exception back to A, and then A knows about it. So these are ways we've built up methods. Garbage collection helps avoid this memory leak problem that occurs when you bomb out of an internal structure without cleaning up after yourself, right? There's some additional concerns here, but I've offered some of those in brief here. Once again, I would note this difficulty of composing into higher order functions. Maybe you don't remember that, but this was this whole issue. And here I've put in some quite modest pipelines. You take a look at something like this, which is many successive modular components strung together. First do this, then filter, then group by, then map the values, and then turn into a sequence and sort with this. And you get successive components. If one of these bombed out with an exception, the whole thing is over. Like the whole pipeline is over. And you might not know from the exception, where did I bomb out? Maybe you fix things up. You say, oh, that database is down. We'll go to this other database. Now I'd like to continue in this pipeline, and you're out of luck. You're out of that pipeline. You bombed out of there. You can't go back and sort of say, hey, resume now. I fixed up everything. No, you've bombed out. And so you're in a situation where you have difficulty composing these elements. And once again, and with higher order functions, you're going to have issues in using them with exceptions in because they may throw an exception you're not aware of. So there are ways of using exceptions better and less problematically in ways to reduce these risks, right? Like handle them as close to where they're thrown as possible. Translate exceptions into meaningful language for that level. You don't want the user to see an exception which is totally inscrutable for them. It's framed in terms of language. They have no clue what it means, right? We've all seen things like that from systems we've worked with. We get a seg fault, and that's presented to the user at the top level, or some inscrutable timeout messages. We don't know what it is. So part of this idea of sort of having successive handling as it goes up is you consolidate exceptions and you translate them into a language suitable to that level. So as you go up, they become higher level descriptions, which eventually a user may understand. Maybe it just says the system is not available right now. Please try back later, or we will retry within another 15 minutes. Please wait. What have you? Try to use checked exceptions, things that are confirmed as part of the type reasoning, where A knows if B can throw an exception, and if C throws an exception, B either has to handle it internally and not throw it, or it needs to throw it and have it as part of its signature. It's a checked exception, not an unchecked exception. It's part of the type. It's part of the contract that B has when it uses C, and A can count. Excuse me. It's part of the contract that B offers. So when A calls B, it knows what it can throw. Reuse common exceptions. Don't create your own. Document causes for exceptions and include relevant. This says context. It's really it should be it says contact. It should be context within the exception message. So that it gives us a sense where we're going on. And a key principle here, as far as cleaning up, as far as not corrupting data structures, because you bombed out halfway through, the structure was half updated and half not, and now it's corrupted because it doesn't hang together. It's not consistent. You try to aim for atomic operations that happen either all at once or not at all. And there are ways when we deal with transactions through databases, transactional memory, certain types of abstractions we build that guarantee this atomicity. It's as if they don't occur at all, or they fully occur. They don't occur halfway in a state that leaves them, in a state that is untenable, that is inconsistent. Okay, I want to talk now about assertions. I have required none of these other types I've required in your project. This third type I've required. I demand it. I exhort you to have it. And I'll tell you why. So assertions are also a way of handling things that go wrong, handling things that are problematic, that are not according to plan. But they handle a very specific type of things that are not according to plan, things that go wrong. They handle logical errors. They handle cases of programmer oversight, mistakes that should never occur. circumstances which should be impossible by the rules of the game, by what developers should be doing. At least per understanding, this should be impossible. We catch those with exception. In short, they capture our ways in which we're reasoning about the system. So that if our reasoning is off base, we know it as soon as possible because our code is counting on that reasoning. And the sooner we find it, find those problems in our reasoning, the quicker we can fix this situation, either by updating our reasoning. Oh, that can occur. I didn't realize it. I was thinking, inconsistently about it. Or, oh, there's a bug somewhere else in the program that's leading this to happen, this thing that should never happen, and we can fix that. And they allow us to discover these things closer to the source of a problem. So assertions are a type of, you may have heard of defensive programming, building a system that's robust to problems. Exceptions, some return codes, and indeed monadic ways are excellent ways of doing defensive programming. Assertions take the battle to the enemy. Assertions are an instance of offensive programming. Not in the sense of obnoxiousness, of course, in the sense of aggressively going out and finding issues, going out and locating problems proactively. So the goal of an assertion is, if you're going to fail early. If there's going to be a problem, detect it as early as possible, so you can flag it and eventually fix it. If your reasoning is off, you find it as soon as possible so that you can fix the circumstance, whether your reasoning or the problem that your reasoning is detected. So it alerts programmers to misplaced assumptions about matters that are under developer control. These are not about like what the user has done, that the user should never enter a value, outside of, the range 18 to 100 for their age. No, you have to handle user inputs in a way that dignifies users, gives dignity to users. We can't say, we will not handle users who fail to comply. What assertions flag are problems with our reasoning, things that are under developer control and just ain't so. They fail to adhere to what's agreed upon or what our understanding is. They flag occurrence of conditions that should never occur. Okay. We're counting on which we're counting. And by putting them into our program, we secure several benefits. The documents accept assumptions. It makes the code self-documenting to a degree. It's better than a really good comment to the effect of what we're counting on, because it actually checks it, confirms it. It reduces a likelihood that some error will slip through, that the code's going to be modified in a way that breaks our assumption later, or that someone's using it in a way that's contrary to our assumption and we catch it as early as possible. And it does force us to think about handling not just the common case, not just the desired case, not just the typical case, but forces us to acknowledge that it's possible that our reasoning is wrong and to double check it. It reduces debugging time by meaning we detect an error closer to the underlying faults, even though the failure may come from it only much, much later. I mentioned the example of, maybe there's a problem at one point, and if we don't have an assertion, a value be inserted into a database that is an incorrect value. It's an inconsistent value. It's inconsistent with other things. And that's only discovered much later in system operation, totally different types of tests or whatever. And tracing it back to its source might be quite hard then. We can attack that problem upstream, very close to its source. We can nip it in the bud and avoid that long delay where it's in a database and we're just waiting for a test to find it, etc. And we can use assertions to prove the thoroughness of tests. So what I'm alluding to there, of course, is this old mantra. I've mentioned it several times. It's old chestnut that testing finds failures, finds system trouble incidents, and peer reviews and debugging find faults that underlie this. And assertions bring failures closer to the faults because they fail when there's a problem, when they detect a condition that just ain't right. And by scattering them throughout the program, we discover these conditions closer to where they occur. And in each such occurrence, when it signals, hey, something's wrong, that's a failure. So we bring the failure back from something much later, potentially, to something much earlier, close to the source of the problem, or closer. Now, I mentioned these as being in the canon of offensive programming. They're not the only type of offensive programming. There's other techniques like filling memory with illegal values and lower level code, or I mentioned earlier, setting default values to be illegal and enums, for example. There are ways we can build our system so that if we've done something wrong, it becomes obvious soon. But assertions are they're certainly the most prevalent, the most prominent, and arguably the most valuable and generalizable thing within these contexts. So we're seeking to fail early. I've said that. What sort of common errors to be taught? I said to misplaced assumptions, right? Well, one class that we've certainly discussed with teams and in classes, one category of problems is failure to adhere to preconditions or postconditions or invariants in history properties. These latter two we're going to be talking about in the context of Liskov substitution principle. So those are gimmies. Like if you have preconditions, check them in assertion. If you have postconditions, check them in assertions. Or handle them as errors, one or the other two, for preconditions. For postconditions, generally don't handle them as errors. If there's a postcondition that should follow from the preconditions, the fault lies not with someone else, it lies with our own code that took in these things that adheres to the precondition. And if it doesn't adhere to the postcondition, there's something wrong with our code. We need to fix it. So generally, you need assertions for those things for sure, rather than just error handling. Logical oversights by the programmer. You're counting on a data structure having no duplicate entries, having no entries, no keys that are null, or no values that are null, or no values that contain values less than 0. You may check that this value being passed to you is not null, and you declare this should only be passed. The precondition is this should be non-null value. If someone passes it, you want to say, hey, that's not acceptable. Either you need to handle it in an exception, or excuse me, with an assertion, or you want to have a formal error handling for it, which would signal to the caller in some way, hey, you've given me an improper value. Exceptions are one way of doing that, although they're They're often far more far better ways of doing it beyond that. You can test higher level factors as well. For example, an assertion could test does this value return adhere to some obvious properties. If I'm finding this string within that other string, it could check, is that index, claimed index, is it in fact the prefix that's starting at that index really the sought string? Or you could check a brute force algorithm, which might be very easy to write. Does it give the same value as a much cleverer but potentially tricky algorithm to write? You can actually check in an assertion if those two are the same, recognizing that the assertions can be very readily disabled and typically are disabled for shipping code. For production code, they are disabled. So you may check during your development process that the efficient brute force algorithm give the same results. You develop great confidence in it, and the assertions are turned off in production code. Or alternatively, if you want to leave some enabled, that assertion is turned off in production code. Okay, so I'll note that logging, you generally want to use your multi-level logging framework for assertion failures. You want to make sure if there's an assertion failure before you bomb out, you log it at the appropriate error level of logging. And perhaps most importantly here, make sure you're using assertions for logical problems with the program. You don't use them to handle things that are inconvenient, but not under programmer control, not under developer control. An example is memory exhaustion, or disk full, or network disconnection, or corrupted file. These are generally factors which are under control by environmental factors, not purely the dictates of the developer team. And similarly, you don't use assertions to handle user input, unexpected user input. You don't use it to handle, the user has entered a value outside the desired range. You could use it to say, well, did this value that originated with the user, which our code before this point should have checked is within that range. You might assert now it's within that range because that's something under the control of the system of the developers. But you're not going to do it to police user end user behavior. So why have assertions? They may seem perverse, right? You bomb out when an assumption is not adhered to, when your reasoning is off base. Well, it can help, again, track down the source of problems much more readily. If you have assertions sprinkled in the code all along, there's a good chance you may find some whiff of this fault, of an underlying problem, closer to it. And you can follow its tracks back upstream more easily because it'll be much closer. Right? You can, by not going forward with an error, a situation that doesn't make sense, a logical problem in the system, a condition where the rules of the game are violated, where the properties your code is counting on no longer hold. If you continue on, It's deuces wild. You don't know what's going to happen, right? It's Wild West. You don't know what data will be corrupted by this. Your code could end up making the file you're working on permanently unreadable or corrupt the data in some way that deprives the user of at least a stable set of data. And particularly if you have some sort of transactioning, by failing, you can roll back to a consistent state. You get this atomicity guarantee where this failure's occurred and now it undergoes rollback, and it's just as if you never started to work with the data. It needs to be emphasized that particularly if you're dealing with production code, there are costs, right? If you have assertions being thrown in code that is being run for end users, you may drive away those end users, right? And that may end up making them think less of your system. Now, whether it's maybe that's the least of the evils. Perhaps if they had continued to use this system, they would have been even more grievously unhappy because they wouldn't have been able to open their documents anymore, or because their database would have been rendered inconsistent with incorrect data, and they'd be making decisions based on incorrect data, which would be far worse often than having a nuisance formed error message. But often we eliminate assertions from production code with the assumption being that they've served their purpose. They have helped us find these underlying faults. We have developed great confidence in the system's correct operation, and we wish to spare the performance costs and the risk that they will lead to unexpected behavior at runtime. Now, given that assertions are generally taken out of code, there are some things you want to avoid, right? You want to avoid mixing side effects with assertions. Like here, you're asserting that this value, which you pre-increment first, is less than some maximum value. This is not good, because when this is stripped out, you're not going to have this logical step of incrementing it, and your program might then encounter errors. You don't want the removal of an assertion to change the behavior of the program. So, how are assertions used? I'm going to give you some examples. I'm expanding on this because there's a lot of interest in how to use this assertions in your code. Well, I've mentioned that specifications for code can come in different forms: preconditions and postconditions. And yes, for classes or larger structures, invariance and history properties of structures with state. But another way is preconditions, returns, and modifies, for example. So here we have a function that takes an array of type 1, an array int1, an array r int1, array of int1, and a corresponding length, and then same thing for array of int2 and a length of int2. And here we have a precondition. They're either of equal length, so they're either both null or they're of equal length. So either both are null, because we're finding the first differences between these two arrays. They have to be of equal length here, and we're going to check, are their lengths either both their lengths are equal or both are null. We could do that, and here's one in C. normalizing an array. Okay, I have an array of doubles and a count of elements, and I want to normalize that array. So I want to divide each element of that array by the sum of the array. But the preconditions is each and every element in the array has to be greater than or equal to 0 in value. And more than that, maybe some of those elements are 0, but their sum has to be greater than 0, because I'm going to be dividing, I'm going to be returning an array whose values are the same as the original array's values divided by the sum of that original array. And if this sum is equal to 0, we're in bad shape. So here we have preconditions on these values in the array that each and every element has to be greater than or equal to 0. And they have to sum up to something actively bigger than 0, not equal to, or else we got to divide by 0, right? And so here I put in assertions, okay? First of all, the count of elements is also stated. If the array is not null, the count of elements is greater than or equal to 0. And we assert that the minimum is greater. This should say the array minimum should be less than or equal to or greater than or equal to 0. We do allow zeros there, and the array sum is strictly greater than 0. So this is translation of these preconditions into a form where we have assertions that check these assumptions. These are part of the contract. If you are calling me and you're not adhering to your contract, I'm going to throw an assertion that indicates a programmer error somewhere else in the team or somewhere else in the, whoever is using this. Maybe it's myself and I forgot to adhere to these, or maybe there's a problem, there's a bug in that code, and I can spot it here. Additional examples here. Identify index. So here, we're looking for a point in this array, this int array that matches the value I'm looking for. I want to make sure that the array is not null, and that the count of elements is greater than or equal to 0 here. Notice that this does use a return value to signal it's not found. It's like the find first. There's another case of an assertion. Here's a replace. It says, okay, hey, look, we're going to replace here within our internal data structure. This is in a class where we have an array called values, an int array, and we want to replace an instance of a val in that array, something whose element, an index that the element whose element is val. We want to replace that element of the array with n val. And the idea is value always has to be current, so this val must always be present. If we're counting on that, this should always be reached. We should always find one element, at least one element. There should be at least a first where we have an element of value, the values array that's equal to val. It says it's always must be present, in which case we'll replace it by n val and we'll leave. So if this precondition is met, we should always leave with this for one of these indices of the array. One of them should yield this return value, lead us to leave. Should find it and return. If we get down here, we haven't found it. We somehow haven't returned here. That's a sign it wasn't in there, and then we assert false. We say we can't find it. It's contrary to the preconditions here, and we want to signal that to the user. So maybe I'll ask you in the closing minutes here. What's wrong with this code? Anyone? malloc. You may remember that allocates memory. What's the problem with this code and how it uses assertions? What's the problem here? It says if the assertion hits, the memory isn't freed. It is true that it kind of bombs out, although assertions generally stop the program. So concerns about memory being freed is not so much of an issue here. There's actually a deeper issue here. What's the problem? And actually, this assertion is hit before we allocate memory. This assertion is hit after we allocate memory. But when does this assertion fail if what is the case? This assertion fails if what is the case? So we're asserting that this is true. The assertion will fail if what then? If str_new is what? Okay, the case where str_new is null. Right, it's not an error. So the case where str_new is null, which is what this is, this will fail. Str_new equals null. That's not a problem of the programmer. The programmer can't say, let there be memory. That if there's no memory, I'm out of here. Like I'm sick of it. You can go to hell. Like that's not acceptable. That's not acceptable. A mature programmer, and I trust you all be mature programmers, all be professional. It has to handle cases where inconvenient things happen, including that there's no memory left. So the mature thing is to test if it's null. And hey, if this is null, we need to signal it somehow. And here it signals it in C with returning a distinguished value, null, that you trust that the person who calls you will clear up. If this was a language with exceptions, we could throw an exception. If it was a monadic value, it turns out we could return a maybe whose value is nothing. Okay. Unfortunately, we're out of time. I really regret that I'm not able to be there in person. I hope to be back by Thursday. I seem to be making it through much of today without taking time off for bed rest, which is good. And I appreciate you bearing with the remote lecture. We are slated to talk with the final ID3 review today at 4:00 for the tutorial slot. And right now I'm hopeful about that. And I would ask that Team 1 just keep their eye out on announcements. I will post an announcement if I'm not able to, and I have to seek the comforts of the cave of Morpheus. Thanks very much. Take care there, and I look forward to seeing you on Thursday.